Okay, folks, I've got a few minutes past, so maybe we should go ahead and get started. Let me see how many we got online. Okay, looks like we've got a quorum. Okay, so starting off with some logistics, I graded and returned everything that I had in my hands as of Monday. I hope you guys enjoyed the long weekend. I know I needed it. So we have got almost all of the homework 2s graded and returned. I've got 12 out of 14 of those, and I'm in contact with the last couple of students. I should be able to have the solutions posted soon. Homework 3, I graded and returned the ones of those that I had in hand. That's 6 out of 14. Homework 4, I posted at the end of last week. It is not due until the end of next week. So this week is a catch-up week. I hope that gives people a chance to fill out some of the things and not slip too far behind. I will go over the new content of the homework assignment momentarily about the hydrogen atom. We're also making pretty decent progress through the schedule for the semester. So I think it's time to start thinking about what midterm number 1 is going to look like. That could be somewhere in the neighborhood of 3-ish weeks from now. So it's going to take maybe a week, week and a half if things get slowed down, maybe 2 weeks to work through time-independent perturbation theory, which is what we'll start next week. And then after that is a nice logical break to stop and have a midterm. So we should start thinking about what kind of format would be useful for the midterm, whether we want to do some kind of take-home midterm, similar to how we did the final last semester, sort of like a super homework. If we'd rather have something more modest in scope that's to be done during the class period, something like that. So I'm pondering questions about the midterm. If you guys have thoughts on that, I'd like to hear it. Any questions or comments on logistical issues before I advertise what's on homework 4? Yes, sir.
The thing about the midterm, if it's take home, it's more like the students who don't come to the class or cannot come to the class, they would get a chance to do it, or?
Yeah, so my thought was either I could do the midterm the same way I did the final last time, where you would have like a week to do it. It would be a longer assignment, like a super homework. Or I could do something which is intended to be done in about 1 hour. I would still put it on Canvas. You would still upload it. If you want to come to class and have me here in front to ask questions, I'll be around. If I was going to do that, I would post it online and have it appear right before the start of our scheduled class, give you an hour and 15 minutes to work on it, and then give you like an extra 20, 30 minutes to upload the solution afterwards, something like that. That's sort of what I have in mind. So if you guys have opinions about that, if that would work, if that would not work, let me know. That's just what I'm thinking about. Any other thoughts or questions, especially around what that midterm might look like?
The super homework is a higher chance of success, put it that way.
A higher chance of success? I mean, very different expectations. Like if you have a week to do it, then I'm going to expect you to flex all of the muscles, show all of the analysis, pretty comprehensive for what we've covered so far. If we were going to do something of a much more modest scope in class, that would be more like the small calculations in the homework, like the first problems of the homework, and not like the second problems of the homework, which are the longer derivations and applications. I was thinking maybe even some like multiple choice questions at the beginning on conceptual things. I don't know. We can think more about that when we get to it, but either way, when it comes time for the midterm, the class before, I would like to give you a preview, a sample exam to show you exactly what kind of things I would like to be on the midterm, what the format would be like, solve it in class. I don't want there to be any mystery or surprises for you.
Okay, that sounds wonderful.
That sounds reasonable? Okay.
Yeah, having a preview of the exam is very...
I don't get any thrill out of surprising people. There's no benefit to your learning if I shock you with something you're not prepared for. I want you to see exactly what's coming, know exactly how to prepare for it. Oh, that's also why I wanted to mention this. So this is related to this. It's very important to me. I want to make sure everyone has the correct solutions for the homework to study by in time for the midterm. So as we start to get closer to the midterm, I'm going to have to start imposing cutoffs on homeworks to make sure that I can release all of the solutions in time for people to study by them for the exam. So I'm trying to balance giving people enough time to get caught up and making sure you have study materials that you will need for the midterm. Okay, any other logistical questions or concerns? If you have opinions, please feel free to email me. Let me know what you're thinking about this stuff. Okay, if not, let me share screen momentarily and we will preview briefly homework 4. All right, you guys seeing my screen?
Yes.
Okay, so this is homework 4 on the hydrogen atom. It is not due this week, it is due next week. So you've got some time to catch up. Just like everything else, it's 2 problems long. This first problem is honestly really, really easy. Everything in this first problem is actually undergraduate level quantum mechanics. I looked through the comprehensive exams, and honestly, they're not asking very much about the hydrogen atom on the comprehensive exams. To the extent that it showed up at all, it was very basic calculations. So I stole those problems, and the whole thing is basically like an undergrad QM problem for you to work through. So this is my present to you, calculate some numbers. So just a reminder for those of you who have not seen this in a while, when you're talking about transitions in the hydrogen atom, the energy of the photon, which is associated with being absorbed or emitted during an atomic transition, is related to the difference in the energy levels. So you can answer questions about what is the wavelength of the photon emitted or absorbed? What is the energy of the photon emitted or absorbed? There are names associated with this, the Lyman series, the Balmer series, the Paschen series. Hopefully these are things that you've heard before in undergraduate quantum mechanics. For your convenience, I give you a table of masses and charges of various particles, the proton, the neutron, the electron, the positron, and the muon. And all that I'm asking for, so you see a bunch of 1-point exercises. These are calculate some numbers. The only real theory exercise is here in the beginning, and that's not much of a calculation. This is show that if you have 2 particles of different masses, that you get the same Hamiltonian we solved in class, but with a reduced mass, and potentially with a different charge z instead of just plus e and minus e. Again, this is undergraduate stuff, not a big deal. So don't stress about this. This is really, really easy. Just show that you get the same Hamiltonian back with different numbers, and then plug in for different particles. So in class, we treated the proton as static. We did not consider the kinetic energy of the proton. If you include the kinetic energy of the proton, there is a small correction. So calculate for me that fractional correction from keeping the mass of the proton instead of locking it in place at the origin. Similarly, this was a problem, a sub-problem from the 2019 comprehensive exam about the difference between the energy levels in hydrogen versus deuterium. Deuterium is 1 proton and 1 neutron. So again, you'll calculate just some numbers using this formula. This was another older question that I found that was asking about positronium. That is a bound state of a positron and an electron, matter and antimatter pairs. Again, same formula, plug in some numbers. I made up my own question involving Z not equal to 1. So calculate the Balmer beta transition of the lithium 2+ ion. Again, just plug in some numbers. This is actually relevant for current research in nuclear physics. I put in a link here to the proton radius puzzle. Yes, thank you. This is an important question where you get apparently a different number for the measured radius of the proton when you measure it with a muon compared to when you measure it with an electron. It's a very interesting question in nuclear physics. And that's related to the fact that the muon sits much, much closer to the proton than the electron does because it's heavier. So I ask you to calculate the ratio of the ground state radius of the atom. That's the radius of the muon distance from the proton compared to what the electron would have been. You see that the muon is sitting much closer to the proton than the electron is. And I spent a lot of time on Wikipedia looking up reasonable numbers to give you for this. You can use the difference between the known value of the wavelength of certain atomic transitions and the observed value astronomically to calculate the redshift of distant astronomical objects. And based on Hubble's law, you can calculate how far away they are. So this is an actual galaxy, which was described on Wikipedia. If you measure the Lyman break transition with this wavelength, that is not the true wavelength of the transition. That wavelength has been redshifted according to the relativistic Doppler formula. So if you know the true value, you have the measured value, you can figure out the velocity of the distant galaxy. And then from the velocity of the distant galaxy and Hubble's law, you can calculate the distance. If you calculate the distance, you can even compare it more or less with what you find on Wikipedia, and you should get about the right answer. So nothing particularly mysterious or complicated about problem 1. Problem 2 is a bunch of algebra. So it is not hard, but it is very easy to get lost. So we will go through a version of this in class. At the end of the day, all I'm asking you to derive is one formula. Derive this. We're going to take the vector that we discussed in class, and you're going to square it. Classically, when you square it, you'll get this thing with L squared Quantum mechanically, when you square it, you get plus h bar squared from all of those commutators. And getting those plus h bar squared from the commutators is a bear. So there is a lot of algebra to work through, and I've tried my best to give you as many tools and techniques as possible to guide you through that. We will use many of these things in class today on a simpler example to show how it works, and then hopefully it will not be so mysterious for you. So I'm reminding you things about angular momentum is the generator of rotation. So if you have an object that is a scalar, you know that it commutes with the angular momentum. If you have an object that is a vector, you know how it commutes with the angular momentum. If you have commutators involving the momentum operator is easily written as a derivative. So if you end up with commutator of momentum with something ugly, my advice is write it as a derivative of the ugly thing. That's easier than trying to calculate it in some roundabout way. We will have an example of this in class. Normally, x and p do not commute if it's the same x and the same p. But if you have x and py for different values, they do commute. So when you see something like this, where you've got ripj with epsilon ijk, only different combinations of x and p show up. So these guys do commute, even though x and p generally do not. Finally, this is another example we'll work through today. If you have an anti-symmetric combination of a symmetric thing, it is 0. So if you have something like epsilon ijk, ri rj, Ri and Rj commute with each other. You can write it in either order. It is beautifully symmetric. You put that together with an anti-symmetric object, you get 0. But you got to be careful about how you implement this in quantum mechanics because there are commutators. So this is just a toolbox. Most of these things we've seen before. We will use that today, and I'm just reminding you of it. Here is the thing that I'm asking you to prove. I'm asking you to derive this formula, and so I try to work it out for you in steps. The very first step is take the vector and multiply it by itself. There are 4 terms. You get a squared, b squared, and cross terms. F is the a squared. This thing, which is simple, is the b squared, and this is the cross terms. So show that you get, this is the general structure of the ugly thing from a squared. This is the general structure of the cross terms. This is a very simple identity that you will want to use as often as possible to simplify your life. Show it. We will show something very similar in class. Then the main exercise is, okay, evaluate this first thing. You've got a bunch of terms, you're going to get a bunch more. You have to systematically commute things. So my advice to you is there are lots of terms, but don't panic. Most of those terms are 0 for one reason or another. Use your properties and get rid of them. You know things about how angular momentum commutes with scalars, so try to assemble these things to make scalars wherever you can. Also evaluate the cross terms. This is what you should get. It looks complicated, but I recommend that you systematically try and commute L to the right and R to the left. If you do that, you'll get various combinations and commutators. Keep an eye out for the ones which combine to form L. As long as you stay organized, it's not too bad. And then once you have this expression and once you have that expression, you're done. Just plug them in together and show that this gives you the answer. So this is a lot of algebra. It's easy to get lost, but it's actually not that hard. Just try to stay organized. Okay, any questions or comments about homework 4 or other logistical issues?
I liked your link to the proton thing from homework. That was cool.
Cool. Yeah, I hope it's useful. We have no idea why the electron sees a different radius of the proton than the muon does. Could be an experimental error. It could be undiscovered particles. It could be nuclear physics is complicated. Nobody knows the answer. So,
which one is more accurate?
Your thoughts? All right, anything else before we finish up the hydrogen atom today? Okay, great. If not, then let's remind ourselves what we've talked about before. Previously, we solved the hydrogen atom with brute force using series techniques. We found the energy levels of the hydrogen atom went as 1 over n squared. We also found that there was a significant level of degeneracy among the energy levels. That degeneracy goes like n squared at each level. So this is my energy level diagram, E versus n. The ground state is down here. That one is unique. The first excited state, n equals 2, has 1/4 of the negative energy, and there are 4 of them. There's L equals 1 with 3 different Z states, and L equals 0. For the second excited state, you've got 9, and that degeneracy continues to increase. It was not obvious from the series solution method why this degeneracy exists or where it comes from. So in preparation for discussing that, we talked about the classical 1 over R potential, the Kepler problem. And we said that in general, 1 over R potentials are special. They have an extra conserved quantity, which is sometimes called the Laplace-Runge-Lenz vector. That is defined as this A object. It is P cross L minus M times some constant K and then the unit vector in the radius direction. K here refers to whatever the coefficient of the 1 over R potential is. So this describes the Kepler problem with gravity. This describes the hydrogen atom. Any 1 over R potential has this. And the advantage is that the Runge-Lenz vector is a conserved quantity so that dA dt is 0. We will use that today to rederive the hydrogen spectrum algebraically by quantizing the Runge-Lenz vector in the form that you see on the homework. And this will explain the origin of this degeneracy as rotational symmetry in 4 dimensions, not in 3.
Is there a reason in particular that you write the unit vector as R vector over R rather than just like R hat?
Yes, it's because since we're talking about quantum mechanics, I'm really trying very hard to keep hats to be operators. So I'm avoiding calling the unit vectors with hats.
That makes sense. Thank you.
Sure. Let me crank up the volume so that I hear questions better. Okay. So before we go to the quantum Runge-Lenz vector, I want to mention a couple of properties of the classical Runge-Lenz vector. So first off, its conservation defines the equation of the ellipse. Defines the orbits. So by writing dA dt is equal to 0, you are actually solving the Kepler problem. We have A is P cross L minus MK R over R. If I take A dot product with the position vector R, this is magnitude of A, magnitude of R, cosine of theta. This is P cross L dot R minus MK R over R dot R. In this first term, I can cyclically permute the triple product. This is the same as R cross P dot L, which is nothing more than L squared. This second term, R dot R, is R squared, and I cancel out 1 power, minus MKR. So I have AR cosine theta equals L squared minus MKR. And if I rearrange this equation, I get the equation for an ellipse. So this equation describes an ellipse. And this coefficient in front of cosine theta is the eccentricity. This is just for your information. What is the significance of the Runge-Lenz vector? It is tantamount to solving the Kepler problem. If you know that A is conserved, you know that the eccentricity is constant as a function of time. It points in the same direction. It has the same magnitude. All right, second property. Conservation of the Runge-Lenz vector only adds 1 condition, not 3. You would think if I have a 3-component vector that is conserved in addition to everything else, I have 3 new constraints that my physics must satisfy. But actually, 2 of the components are dependent. So there are 2 constraints that the Runge-Lenz vector satisfies. For one, you see immediately from its definition A dot L is equal to 0. If I take this in dot product with L, this cross product is already perpendicular to L. L is already perpendicular to R, so I trivially get 0. This is one constraint on the Runge-Lenz vector in terms of another conserved quantity you already have. The other one is to calculate the square of the Runge-Lenz vector. So this is E cross L minus MK R over R dot E cross L minus MK R over R. This is essentially the classical version of what I'm asking you to do for homework in problem 2. So when you open up the parentheses, I have P cross L dot P cross L. I have the cross terms, minus 2 P cross L MK R over R plus M squared K squared R vector squared over R squared. This quantity is 1. So again, I can permute the triple product here. This is R dot P cross L. This is again L squared. This one, I'm going to interpret this as, let's see. So this is L cross E cross L dot P. Right, so this is a triple product A cross B dot C, and I can permute the triple product if I consider this one object. So I permute it to the left, L cross L dot P. Now inside I can use the back minus cap rule. Inside this is P times L squared minus L times L dot P. Dot P. L dot P is 0. Angular momentum is perpendicular to linear momentum. And then I have P dot P, which is P squared. So when I square this thing, I get A squared equals P squared L squared from the first term. From the cross terms, I get minus 2 MK L squared over R plus M squared K squared. Both of these first terms have angular momentum in common. I'm going to pull out a factor of 2m, P squared over 2m minus K over R, L squared, plus M squared K squared. The quantity in parentheses is the energy, i.e. the Hamiltonian. There are two constraints satisfied by the Runge-Lenz vector. So by conserving it, we do not add 3 quantities, we only add 1. This property we will derive quantum mechanically how it works. This property I'm asking you to derive on the homework quantum mechanically how it works. It is more or less along these lines, but it's a lot hairier to derive by doing all of the yucky commutator algebra. At the end of the day, the only difference that you get is when you put hats on everything, right? Energy is called the Hamiltonian. The only difference is that you add a plus h bar squared in there. That comes from all of the commutator algebra of everything involved here. But when you go through this exercise on your own, you should identify the same kind of terms, right? From that first term, you should be seeing P squared, L squared come out of it for essentially the same reasons. From that cross term, you should be seeing L squared over R come out of it. And that's how you're going to pull out the energy. Okay, the most important property for the derivation that we will do today is that the Runge-Lenz vector acts like angular momentum. Right, so if I define a vector, I'm going to call it D, which is A divided by square root 2m absolute value of the energy. So if A squared is 2me L squared, if I divide by 2me, then that scaled quantity has units of L squared. Right, so I'm saying A squared over 2me equals L squared plus mk squared over 2e. So this combination has units of angular momentum. So if I take the vector itself and I divide by one of those things, divide by the square root, remembering that the energy of a bound state is negative. If I divide by that thing, this is essentially some kind of angular momentum. And we know something about the algebraic properties of this new effective kind of angular momentum. Because it is conserved, since dA dt is equal to 0, obviously derivative of this scaled Runge-Lenz vector is also 0. This means that it has 0 Poisson bracket classically with the Hamiltonian. And this means that when we go quantum mechanical with it, di with h will be 0. These things will commute with each other. This is going to be a good quantum number, just like it is a good conserved quantity to describe my states. What does this do? I'm not going to derive all of the algebra behind this, but I want to give you a preview so you have some sense as to how it works before we dive into the quantum part of it. Effectively, what happens is that the addition of this D kind of angular momentum enlarges the rotation group. So you go from 3D rotations. The group is SO3, and this is generated by L, generator of rotations in 3 dimensions. What you obtain is 4-dimensional rotations. The group is SO4, generated by both L and D. It's beyond the scope of what I have time for today to derive exactly where this comes from, but essentially what happens is you create a 2x2 matrix. Sorry, a 4x4 matrix, excuse me. So this is a generalized version of angular momentum. So something like x mu P nu minus x nu P mu. So anti-symmetric combinations of position and momentum. This is how you build angular momentum L. You can also understand the Runge-Lenz vector as being built in a similar way. To make this precise, I've got to rescale all of my coordinates and redefine what x and p are. I'm not going to go into that. But what this effectively gives you is a rank 2 tensor. It's anti-symmetric, so it's 0 on the diagonal, and it has components. So if this is, the 0 component, and this is x, y, z, the angular momentum is mixing x, y, z, and x, y, z. So this is LZ, LX, negative LY, and it's anti-symmetric. So that's right. According to my notes, I have my signs backwards. And then the Runge-Lenz vector, the scaled Runge-Lenz vector, fills in these extra components to complete this to a 4x4 matrix. So this is how the two kinds of vectors combine and play well together to build effectively a combined 4x4 matrix that acts like hyperangular momentum if you wanted to give it a name in 4 dimensions. Part of why I'm showing this to you now is that something very, very similar happens when we talk about relativity. When you introduce 4 dimensions in relativity, you can think about Lorentz transformations and boosts as rotations of space and time. And in exactly the same way, we can construct a 4x4 antisymmetric angular momentum tensor that generalizes the spatial angular momentum together with the special relativity angular momentum that rotates space and time. Okay, that's it for the classical around the lens vector. Now let's quantize this thing. We have a general purpose tool of canonical quantization that tells us how to take a classical object and quantize it. Classically, component of the around the lens vector AI is epsilon ijk pj L sub k minus mk ri over r. And here, for the sake of my own sanity, I'm starting to use the Einstein summation convention. Please tell me that you guys have seen this in other classes. Okay, thank God. So repeated indices are assumed to be sum. Otherwise, it just becomes very unwieldy. All right, when we quantize the around the lens vector, I'm going to put hats on top of everything, but it's a little bit trickier than that. Because classically, I can write this thing in either order and it doesn't make a difference. Quantum mechanically, it does. P and L do not commute with each other. So the standard prescription is when the ordering is ambiguous, you take a symmetric combination of the two. So when I write down my quantum mechanical around the lens vector, I will write AI hat equals 1/2 epsilon ijk. The first term is pj lk plus the same things in the other order. lk pj minus mk ri over r. Both of those are operators. That 1 over r is rather uncomfortable to work with, but it's true. So this object is a little bit awkward as well. Here I have ijk, jk. Here I have kj. So it's a little bit cleaner if I take this term and I redefine j and k. Then it looks like a correctly ordered cross product, and when I switch the order of the Levi-Civita symbol, I generate a minus sign. 1/2 epsilon ijk pj lk minus lj pk minus mk ri over r. So now it should be clear why the algebra of the quantum mechanical problem is a lot more unwieldy than the algebra of the classical problem. For one, now I've got 3 terms hanging around instead of 2. For another, the order of the things matters, and you've got to worry about all possible commutators that can arise. Okay. But we know something about the algebra of the around the lens vector. I think I need a full board for this. The thing that makes this useful is its nicely balanced algebraic properties. So one thing that I know to start off with is commutation with the Hamiltonian. The Hamiltonian commutes with the around the lens vector because the around the lens vector is conserved. Likewise, the Hamiltonian commutes with the angular momentum operator because angular momentum is conserved. I know how angular momentum commutes with itself. Lij is IH bar epsilon ijk lk. You form a nice closed triad when you rotate among different components of L. I also know something about the commutation of AI with LJ. Because even if I don't know anything else, without calculating it by hand, I know A is a vector. And I know how angular momentum rotates vectors. It is always the same. This is IH bar epsilon IJK A sub K. Angular momentum as the generator of rotations rotates A between its various components. The one that is not obvious and that I have mercy to not ask you to prove for homework is the commutation of AI with AJ. This is minus 2mh, a little bit of space. Times IH bar epsilon IJK LK.
And we could just take that as a given for the homework?
Yes, well, I don't know that you need it.
Oh, okay.
I can't immediately think of how you would need it. Maybe somehow, probably I would advise to not try to use this as a shortcut to solve problem 2. I think probably if you do that, that's equivalent to assuming the answer. I don't know, I have to think about it. Hopefully you shouldn't need it.
Okay, and the second commutator, that's an AI, right?
Yeah, so this is AI LJ, that's right.
Okay, thank you.
Yes. So these ones definitely for sure. These are things that I comment on and remind you in the toolbox for problem 2. All right, so this is the commutator algebra. You can see why these guys are starting to play nicely with each other. Aside from that unfortunate factor, which we're going to scale away in a minute, it looks like A and L are acting like similar kinds of angular momentum, but they kind of are all scrambled up. Commutator of A gives you A, commutator of A with itself gives you L, commutator of L gives you L. So this exercise is going to be rescaling A and then unscrambling this commutator algebra. Before we do that, we know that although A is conserved, there are only two constraints on it, so there's only one independent condition. So constraints on A. So first, we know that classically, A dot L is equal to 0. Quantum mechanically, that is not immediately obvious. A dot L equals, by definition, this is AI Li. And I'm going to work through this example on the board as a preview of what goes into calculating these kind of things on the homework. So AI is 1/2 epsilon IJK PJ LK minus LJ PK Li. All right, one thing that we're going to want to use very quickly before we start unscrambling this thing is that let's see that R dot L quantum mechanically is equal to 0, the same way it is classically. Why is this so? This is R sub I, L sub I. L sub I is epsilon IJK. I have the Ri from before, Rj, Pk. This is what I was alluding to in the homework. You have a combination. This guy is symmetric between I and J. This guy is anti-symmetric between I and J. That's going to give me 0. How does it work? R dot L operator equals, we have epsilon IJK, Ri, Rj, Pk. So I want to show that this object is equal to its own negative. So for one thing, I can write the same thing and redefine I and J. Swap I and J. So this is epsilon J I K. I redefine it here and I redefine it here. Rj, Ri, Pk. This is very similar to that. This Levi-Civita symbol differs by a minus sign, epsilon I, j, k. Ri and Rj commute with each other, so I can swap them back and put them in the other order. Ri, Rj, and I still have pk sitting on it. So this object equals negative itself, and therefore this object is equal to 0. That's what I mean when I say a symmetric combination or an anti-symmetric combination of a symmetric thing is 0. In practice, for the homework, I don't expect you to derive this every single time you want to use it. But I want you to understand when you see a combination like this, epsilon ijk, ri, rj, that is automatically 0 for this reason. For the homework, I asked you for like half a point to show that the same thing works when you put it together with p instead of with r, for the same reason. Okay, so that's one elementary property that we're going to need when we start unfolding this combination here. So continuing that. A dot L is 1/2 epsilon ijk. Let's see, what am I going to do next? Let's open it all up. So this is pj lk li minus 1/2 epsilon ijk lj pk li minus 1/2 1 over r ri li. So we just showed that r dot l is equal to 0. That immediately lets me kill this last term. Now I've got to deal with the fact that I've got L's and P's all scrambled up here. So what I'm going to do is I'm going to simplify, let's see, the first L. So I'm going to replace this L with its definition. I'm going to replace this L with its definition. So this is 1/2 epsilon ijk. This one is another epsilon, epsilon klm, pj, rl, pm, li. Same thing with this other guy. 1/2 epsilon ijk. L sub j is epsilon jlm. RL, PM, PK, LI. So just to make sure everybody online sees this, I have epsilon ijk, epsilon klm. Second term is epsilon ijk, epsilon jlm. That came from lk and lj. So now I've made the situation even worse, because now I've got even more objects. But I can clean it up by using the properties of the Levi-Civita symbol. This guy has a repeated index, k, so I can sum over the repeated index and use the identity of the Levi-Civita symbol to simplify that. This one has a repeated index, but it's a different repeated index. This one is j. So when I do that, I get a combination of Kronecker deltas. A dot L equals, all right, so my first term, I had 1/2. When I sum over K, you get one combination of Kronecker deltas that matches the indices in correct cyclic order. This one is KLM and KIJ. So if I match them up in the same cyclic order, I have I and L, J and M. Delta IL, delta JM, minus the wrong combination. Here I have LM. If I go backwards, I have JI. So now I have delta JL, delta IM, right? I switched the pairing. This multiplies PJ, RL, PM, LI. Minus 1/2, same shebang for the second term. Now I'm summing over J. The cyclic order is JLM, JKI. So I match them up in correct cyclic order minus the wrong order. So when I do that, I get delta KL, delta IM, minus delta KM, delta IL, RL, PM, PL, LI. Things get worse before they get better, but now they're going to start getting better. I have now 4 terms, but each of these is now contracted. So I have 1/2. So the first term, I'm going to use these Kronecker deltas to get rid of L and M and set them to what they're equal to. In this first term, I have PJ, RL, but L is equal to I, RI. PM, but M is equal to J, LI. Minus 1/2 PJ, RL, but L is equal to J. PM, but M is equal to I, LI.
Dr. Sievert, in the bottom right of the blackboard,
Yes.
It looks like it's PMPK, but on the top left you have PMPL in the last term.
Ah, yes, thank you. Can't read my own handwriting. Yes, RMKI. Thank you. That's probably going to explain why this is not right. Right. So, actually, that was this first term, so that one's probably okay. 1/2 PJ, RJ, PI, LI, minus 1/2 RK, PI, PK, LI, plus 1/2 RI, PK, PK, LI. Okay, I've got a big mess, but I can clean it up. This piece is P.L. P.L is 0 for the same reason R.L was 0. This is the one that I'm having you show for homework, equivalent to what I just showed here. This combination is 0. This combination, PK, is P squared. So this is RI, P squared, LI. In general, these things don't commute, but P squared is a scalar. So I can move Li past P squared and write this as Ri Pi P squared. Excuse me, Ri Li P squared. And R dot L is 0. So this second term is also 0. Now I have something similar here. This one wants to be R dot L. See, I have a scalar trying to form, and when I get R dot L, I get 0, but I've got to commute it past first. So I'm going to get a commutator. Same thing here. I've got PI that wants to combine with LI and make the scalar P dot L, which is 0, but it's in the wrong order. So as long as I pay the price of introducing the commutator, I can form those scalars. And those scalars are 0. Let's see, so I got rid of this one. Oh, actually, I can do one better here. I have PI and PK. P commutes with itself. So this is the same thing as, let me write it in a different color. RK, PK, PI, LI. I just switched the P's. They commute with each other just fine. This is P dot L, which is also 0. Okay, I like that better. Now I've only got one survivor that I need to kill. A dot L is equal to, so this is 1/2 PJ RI PJ LI. So I'm going to write this as swapping R and P, and then I will pay the price of the commutator to do it. So this is PJ, PJ, Ri Li plus 1/2 Pj commutator of Ri Pj Li. This first term is R dot L, which is 0. Commutator of R with P is I H bar delta Ij. So now I have boiled it down to 1/2 I H bar Pi Li, and P dot L is 0. So you can see it takes a lot more heavy lifting quantum mechanically to derive the identities that were extremely simple to write classically. Hopefully the tools that I have previewed here will be familiar to you when you use them to derive a squared on the homework in the same way. So overall, the properties that we have are A dot L equals L dot A equals 0, and A squared is 2m Hamiltonian L squared plus H bar squared plus M squared K squared. What am I doing on time? 20. All right, let me just draw a line through what we've done so far. If your main concern is making sure that you are able to solve the problems on the homework and on the exam that I'm going to ask you to solve, you can stop here. I am not going to ask you to reproduce the kind of algebra I'm about to do for SO4, decoupling into SO3, cross SO3, yada, yada, yada. This is for your understanding of why the hydrogen atom is the way it is, but I'm not going to ask you to reproduce this under pressure. That stuff, yes. This stuff, no. All right. For now on, let's consider only eigenstates of the Hamiltonian with energy E. So now I'm going to be specifically talking about within a subspace that has a given value of the energy. So that means I'm going to take the Hamiltonian operator and just replace it with its energy eigenvalue. And that A squared I'm going to replace with 2me L squared plus H bar squared plus M squared K squared. And now I'm going to define my scaled operator. dI is defined to be AI divided by square root 2m absolute value of the energy. Remember that the energy is negative for a balanced state. All right, so when I do this, I can immediately write down the commutation relations before. They don't change that much. Li Lj is IH bar, epsilon, IJK, LK. Di Dj is IH bar, epsilon, IJK, LK. Di Lj is IH bar, epsilon, IJK, DK. So now they're all nicely symmetric. This D is acting like an angular momentum and it wants to join its partners. We would like to be able to solve this algebra, and if we were brilliant mathematicians, maybe we could immediately by looking at it. But I'm confused when I stare at this because these are coupled equations. This links D to L, this links D and L back to D, L is linked to itself. I would like to decouple these equations. So this is the coupled algebra of SO4. We will decouple it by defining symmetric and anti-symmetric combinations of D and L. There is no good notation for all of this. Everybody makes up their own crap, so I'm going to make up my own crap too. There is no particular meaning behind the names I'm about to give this. I'm going to call G sub I, defined to be 1/2 Li plus Di. And I'm going to call Fi, defined to be 1/2 Li minus Di. To be absolutely clear, the F and the G that I just wrote down have nothing to do with the F and the G that I name things in the homework. It's just a temporary name. Unrelated to F and G in the homework.
Thank you. That was about to get confusing.
Sure. Okay, so in the interest of time, maybe let me work out one of these and state the other ones. If I take these definitions and I work out their commutators, this commutator algebra decouples beautifully. If I have the commutator of, let's say, Gi and Fj, this is 1/4 G is the symmetric combination, Li plus Di, Lj minus Fj is the other one. So this is 1/4 commutator of Li with Lj minus 1/4 commutator of Li with Fj, excuse me, D, minus 1/4 commutator of Di with Lj minus, plus Li, no. This one is minus, this one is plus. Right, Li and Lj, Li and Di comes with a minus, yes. This one comes with a plus. Di and Lj minus 1/4 commutator of Di and Dj. So when I work out this commutator, Gi with Fj, I get, from the first term, 1/4 epsilon ijk I h bar lk minus 1/4 epsilon ijk I h bar, and then I've got L with D. L with D gives me a commutator which is D sub k. The order that you put them in here is automatically taken care of by the signs of the index and the Levi-Civita symbol. So you don't have to worry about whether D or L came first. It's just IJ, IJK. Next one is plus 1/4 epsilon IJK IH bar. Commutator of D with L. Again, this is DK. And the last one is minus 1/4 epsilon ijk. D with D gives me the commutator IH bar L sub k. And so as promised, the terms cancel perfectly. And G decouples from F. Gi, Fj is completely decoupled. So if I take this commutator algebra and I rewrite it in terms of these symmetric and anti-symmetric combinations, I now get two completely self-contained separated algebras. Gi, Gj is IH bar epsilon Ijk Gk. Fi, Fj is IH bar epsilon Ijk Fk. And Gi, Fj is 0. Two decoupled algebras. Both algebras we already know the answer to. This is regular algebra of angular momentum. So this is the whole shebang of ladders and raising and lowering operators. You already know the answer. So if this algebra in this form is the coupled SO4 algebra, what we have shown is that for specifically the eigenstates with fixed energy, this decouples into two identical copies of SO3. So for eigenstates of the Hamiltonian, that SO4 algebra decouples into something that looks like addition of angular momentum. SO3 cross SO3, two independent copies of the angular momentum algebra group. And beautifully, we already know the answer. Before I write down that answer, let's impose the constraints that we have, because we don't need the maximally general solutions. So we have, for instance, let's see, we said A dot L is equal to 0, and we just rescaled A to make D. So D dot L is equal to 0. So this means when I take these objects, G and F, that are acting like angular momenta, and I square them, G squared. So this is, let's say, G dot G. This is 1/2 L plus D squared. When I open this thing up, I get 1/4 L squared plus D squared plus L dot D plus D dot L. But those cross terms are 0. So this is 1/4 L squared plus D squared. Likewise, when I square the antisymmetric combination F, this is 1/2 L minus D squared. I get 1/4 L squared plus D squared minus L dot D minus D dot L. The cross terms are 0. So it looks like I've got two sets of angular momenta, sort of like L plus S, except the magnitude of this one is equal to the magnitude of that one. So this is like the homework problem you did of 1 times 1. You had spin angular momentum 1 and orbital angular momentum 1. This is telling you they are always the same magnitude in this decomposition. Right, so G squared equals F squared. So now let me write down the simultaneous eigenstates. I can have simultaneous eigenstates of the Hamiltonian with energy E, of the angular momentum operators, G squared and F squared. They have the same magnitude, but they can have different Z components. So I will call that GZ and FZ. So those simultaneous eigenstates are ones that have a well-defined energy, that have a well-defined total angular momentum quantum number that I will call G. And they have two different angular momentum Z components, G sub Z and F sub Z. So that H on this thing is E on that thing. G squared on this thing is H bar squared G plus 1, just like angular momentum on that thing. GZ is H bar eigenvalue GZ. FZ is H bar FZ. So in a totally counterintuitive and hidden symmetry kind of way, we have transformed the hydrogen atom into an addition of angular momentum problem. Between these weird internal angular momenta G and F, and the total angular momentum that you get when you add them together is L, right? So we had G was 1/2 L plus D, F was 1/2 L minus D. So when I add the two together, I get F plus G equals L. So when you think about the hydrogen atom, what this is telling you is that you have effectively two internal angular momenta. I have some angular momentum ladder for F, some internal angular momentum ladder for G. And when I add those together, I will get all possible angular momentum ladders for L. just like an addition of angular momentum problem. So I can have, for instance, G equals 0. If G is equal to 0, then this addition of angular momentum problem is trivial. This is 0 times 0 equals 0. Right? So this means I have G equals 0, GZ equals FZ is equal to 0. LZ is equal to 0. LZ is equal to GZ plus FZ. If G is equal to 0, how is this related to the energy eigenvalues? To see that, we need to plug it into the magnitude condition. This is going to correspond to n equals 1, the ground state. How do I see that? All right, we had G squared equals 1/4 L squared plus D squared, and D squared is the square of the from the lens vector. This is the one that's related to the energy. So I have D squared is 4G squared minus L squared. D squared is negative L squared minus H bar squared minus MK squared over 2E. So I took this and I plugged in for what the square of the Rondo lens vector is. This is the identity that you're deriving for homework. When I plug this in, angular momentum drops out completely. And I can solve it for the energy. Let me write it this way. 4G squared equals minus H bar squared 1 plus MK squared over 2H bar squared E. What are the eigenvalues of G squared? If I apply this to one of the eigenstates, this is 4H bar squared, G plus 1. So I can solve this for the energies. When I do this, I get energy is minus MK squared over 2G plus 1 squared H bar squared. Right, so I cancel out the H bars. I move the 1 to the other side. 4G times G plus 1 is that 2G plus 1 quantity squared divided to the denominator, and I solve for the energies. These are the quantized energy levels. They depend on the total angular momentum G. G has allowed values 0, 1/2, 1, 3/2, ... This number here, n, 2G plus 1 starts at 1, 2, 3, and so on and so forth. This is the principal quantum number of the hydrogen atom. This is telling you the magnitude of that internal angular momentum ladder. So G equals 0, what I just erased here, corresponds to n equals 1, the ground state. G equals 1, a combination of 2 spin 1/2 type ladders, is what makes up the n equals 2 first excited state. So in this way, this explains why the hydrogen atom levels are what they are as an addition of angular momentum problem. It also explains the degeneracy. Right? I have F squared equals G squared, and they both have eigenvalues H bar squared G plus 1. But they can have different Z components. Z is totally degenerate, going from minus G up to plus G. GZ is also degenerate in exactly the same way. Altogether, this is 2G plus 1 allowed Z components for F, the same number of allowed Z components for G. Total degeneracy is the product of the two. That combination is N. N squared degeneracy of the hydrogen atom comes from the internal angular momentum ladders having any allowed components of GZ. What matters is the magnitude of those internal angular momentum ladders. In my remaining 2 minutes, I want to point out what the Rondo lens vector does to your spectrum. So how do you understand this? So if I have G equals 0, that corresponds to N equals 2 times 0 plus 1 equals 1, the ground state. This is the addition of angular momentum problem F plus G equals L. This is 0 together with another 0 equals 0. So I have Fz equals Gz equals 0, and that means Lz equals 0, and this belongs to an L equals 0 ladder. So the ground state, n equals 1, corresponds to L equals 0. That's trivial. The non-trivial part is when I start going to higher ladders. So the first excited state, n equals 2, corresponds to G equals 1/2. So this is an addition of angular momentum problem, 1/2 times 1/2, and this will give me 2 possible sets of total angular momentum ladders, 1 and 0. So I have F and I have G. F is composed of plus 1/2 h bar minus 1/2 h bar. G is composed of plus 1/2 minus 1/2. And when I combine those 2 copies of SU3, I get, for the following possible values of angular momentum, the L equals 1 ladder, plus 1, 0, minus 1, and L equals 0. These are the spectrum of angular momentum states that corresponds to the first excited state of hydrogen. So you have L equals 1, the P wave state, L equals 0 from the summation of these 2 ladders. In the same way, I can do 1 times 1. N equals 3, this corresponds to G equals 1. So this is 1 times 1, and you found for homework, this is 2 plus 1 plus 0. So now for this F type of angular momentum, I have 3 allowed values, plus 1, 0, minus 1. For G, I have the same thing. It's always the same thing. And when I put this together, I get possible outcomes for L. I have the L equals 2 state, plus 2, plus 1, 0, minus 1. This is L equals 2. I have the secondary ladder, plus 1, 0, minus 1. This is L equals 1. And I have the leftover singlet state, L equals 0. All of these are the allowed values of angular momentum L for the second excited state of hydrogen. The point is that the Rundle-Lenz vector, this extra symmetry when written this way, connects the different ladders. We already know how to go from this state to this state to this state. You lower it using L minus. What we don't know is why there's a connection between the different ladders. Why do they have the same energy? It's because they are related to the Rundle-Lenz vector. So these are essentially like, these ladders are a part of a higher dimensional ladder. And by using the Rundle-Lenz vector, you are lowering from this ladder to that ladder to that ladder. And I don't have time to show it, but let me just write the answer. You can use the solution that you know from how to add angular momentum. You worked this out already for the homework. So for instance, I can write down the 300 state. This is NLM of hydrogen. That's talking specifically about this guy. N equals 3, L equals 0, M equals 0. Suppose I have that state, and I act on it with the Rundle-Lenz vector. Let me write D plus. This is X plus IY, the same way we always have that. This is like an addition of angular momentum problem. This is F plus G plus. And if I go from writing L, the total angular momentum, to writing these internal spaces, this is, let's see, Fz equals 0, Gz equals 0. No. Sorry. This is the L equals 0 state. So this is the one that you found for homework. So this one is the one that's normalized to 1 over root 3, Gz equals plus 1, Fz equals minus 1, minus 1 over root 3, Gz equals 0, Fz equals 0, plus 1 over root 3 GC equals minus 1, FC equals plus 1. Yeah, there we go. You have to have the right combination of these Z components that add up to give you 0 and that correspond to the L equals 0 total angular momentum ladder. If I act on it using the standard raising and lowering operators and I look at what I get, when I act on this, the final answer is okay. I get minus h bar 4 over root 3, whatever coefficient, the L equals 1, LZ equals plus 1 state. So the important point is when you do this algebra, you already know everything that it takes. The Runge-Lenz vector is the operator that takes you from the L equals 0 ladder to the L equals 1 ladder. So when I take this state and I act on it with D plus, it takes me from here to there onto another ladder. And if I act on it with D plus again, it takes me from here onto the next ladder. So by raising and lowering in these other angular momenta, you are going from one ladder to the next ladder. They're all part of some weird higher dimensional ladder structure, and you are raising them in different directions. Okay, this is the end of what I wanted to say. This is in Shankar. What's the page number? One sec, I want to give you the page number before we adjourn. So check it out on Shankar, page 422 through 423. He has a different notation for the Runge-Lenz vector. He calls it n, but it's the same thing. So I hope this was insightful. This is not something I'm going to ask you to reproduce, but I wanted you to see algebraically how the hydrogen atom can be understood as addition of angular momentum. You already have all the tools to analyze. Okay, thank you. Next week, we will begin with time-independent perturbation theory. We'll talk about corrections to the hydrogen atom. Thank you.